So why do we need the position of an object in space? There are many applications. A big one we all know is the bin picking system. So bin picking means we have a bin, parts are sorted in, we want to pick them out, or also they are randomly inside. We want to pick them, and we do some further processing with them, like feeding another machine in a downstream task, or something else. Here in the image, we also can see a conveyor belt. Maybe the parts are not in a bin, they are reaching our machine, our sensor system, maybe with a robot, and we want to know the position, to pick them, to grab them, and to do further things. Maybe to bring it another place, or do some inspection. What could it be, inspection? Inspection could be reading here maybe the logo of MVTec. Why do we need the position? Maybe the part is in the conveyor belt like this. So we can pick them, we can move it to a camera, we can do inspection. Also, another thing is doing some measurement. Look, if a previous process had some problems, maybe we milled here the part, and we want to know if our previous machine works properly. So we want to get the distance. So we pick our part. Maybe we have a telecentric lens. We bring it here, and we measure it. And we can tell the system if the part is OK, we have to change some previous situation with a mechanic, or we have to throw it away. It's garbage. It was not manufactured well. Or we'll bring it to the next process. We will feed in. Something else we could do is integration and processing. That means maybe we get the part, and we want to do something with it. This could be mounting something on it. For this, we also would need the position. We maybe could do some drilling a hole. For this also, we know the position. We pick it, we bring it to another machine, we drill holes, or do some welding. So to have the position of an object is very important for many tasks. So be creative. Think about what you can do with our new feature, Deep 3D Matching.
And when we say that it's one of the most challenging tasks, what do we mean? We actually found, finally, an application for all the 3D printers we bought a while back, and that is printing oversized parts for demonstrations. We have a bunch of those printed smaller for the demo over here. We will show them later to you. And some of the challenges already are intrinsic in this part. You can see, for example, that the backside, it was at the bottom of the 3D printer, and it has a different texture and different surface characteristic compared to the remaining parts. Some of the edges are rounded, which means that if we see these edges in an image and the light reflects in a particular way, we will see them not at their correct location, for example. Another thing is, it's not really precisely manufactured. So we have a cut file for this, but the 3D printing has some thermal properties, so I think this is off by a few millimeters. So manufacturing can be somewhat imprecise, the edges can be imprecise, and there are other parts you can think of, like reflective metal, for example. All of these are very difficult to detect in images. Another challenge comes from simply the sheer number of parts. So you can see in the example image up here, when we do bin picking, the objects can be at an arbitrary location, in an arbitrary orientation, and there can be more than one. So we can't really focus on just a single part. We need to detect all of them, or at least enough so that the robot has a few to pick from, literally. And there might be a bin that is in the way, for example. You can also see that some of the parts are hidden by the border of the bin. And finally, we have challenges that come from the environment. So you might have changing backgrounds, for example. Maybe your supplier changes the box color at some point. Or maybe somebody turns on or turns off the light in the factory, which means suddenly the light situation changes. And of course, you don't want to go back to your integrator and ask some engineer to manually change the parameters of your machine vision application. Instead, you want this to work out of the box and to be robust. And deep 3D matching is exactly that. So we've devised a way that uses deep learning to robustly find a plurality of images in arbitrary locations and it's very robust against a wide variety of different challenges that you might come into contact with. So today, we will introduce the technology to you. And there are two key components, really, that define this new method. And the first one is it's a multi-view method. That means we do not operate on a single image, but we use at least two images, at least two cameras that look onto the scene from slightly different angles. And it scales well to a whole bunch of cameras. You can use 2, you can use 10. That's up to you. That depends on your application, really. And Andy will tell you in just a bit why more than one camera is actually a good idea. And the second key component is deep learning. Deep learning, artificial intelligence, it promises robustness, but it comes at a cost. That cost is how do you train this kind of model for your particular object. And we will also tell you how this can be done. And of course, the output is the object poses. So without further ado, why is more than one camera a good idea?
Okay, why do we need more than one camera? Later we will see how it works. So one camera would be enough technically, but one camera has a problem: accuracy. Here in the example, we can see one camera looking with a field of view of a part, but we do not know the depth of the part. So we could find this object quite well and accurate in X and Y, but the Z-axis is very difficult because maybe we have round curves that are not easy to detect, or also we have variation in our product because they are manufactured differently, like maybe a 3D printer in this case with a bad quality, or another like a milling machine. Some parts have variations. So we are in trouble sometimes. And to pick it, robots are expensive, and also some parts also are really expensive, and we need to trust our machine. What can we do? We add a second camera. Now here, it's a triangulation model, and we can see easily that now the depth is not anymore a problem. We can find it very, very well. So we recommend using more than one camera, so 2 or even more. Here, we have another example. We can see a lot of cuboids, but these cuboids look from different angles, different perspectives, quite similar. So to reduce ambiguities and also to have no false positives, we need a second perspective. Here we can see just one side, and maybe on the other side there's something hidden of the part. Here you might have an idea what can happen here, that one part is maybe different. So the first perspective was from the upper left. Now we know a logo of MVTec was hidden. So how could we figure out or find it in space? We need a second perspective to be quite accurate, quite sure. And adding a second camera practically will lead to have quasi no false positives. So that's a huge advantage. And if some parts are hidden, even with 2 cameras, we can add a third, a fourth, so you name it. In this case, we have 2 cameras. We are looking on an object. That's like a stereo sensor looks like. And the only thing we need to have for deep 3D matching is we need to have the same field of view on one object of 2 cameras. Here, with a smallish baseline, this would be very nice for a stereo sensor. Why? Because we have a similar perspective. We can see the same edges, the same textures. And for stereo reconstruction, this would be nice. If it's too small, we will lose accuracy, and in reconstruction also we get in trouble. If we would have a wider baseline also for reconstruction, it's not that easy. The triangulation would be inaccurate, or we cannot see the same objects. This feature, deep 3D matching, does not have these constraints. So we could just use a much wider baseline. Even we recommend it. In this case, we are much more distant, and we have a very different perspective to the object. This gives us accuracy and less false positive detection. But for the reconstruction, this setup wouldn't be very good. So we do not have this compromise. We can add the camera where we want. So in this case, both cameras, we have the field of view, one object. But maybe next to this object, we have a second one that is hidden. Or one camera, the object hides another object. What can we do? We just add a third camera. We have to see the object just with two cameras. But what does this mean for your setup? Maybe you're doing a feasibility study, and with two cameras, you are not as accurate as you want, or you do not have the detection rate, so as many detections. Just add an additional camera. And for the workflow, what does it mean? It's a deep learning feature, so we have a model. You do not need to retrain. So you just use the same model. You just have to recalibrate your system, and after the recalibration, that takes 1, 2, 3, 4 minutes, you're ready to go. You can look at your results. And this is a huge advantage. This is great. This gives us many, many opportunities. And even later, you can add additional cameras, so feel free. Here is another example. We have a larger field of view using 3 parallel cameras. Object 1 is seen by camera A and B. Object 2 is seen by camera B and C. So both objects are seen by 2 cameras. We can detect them both. They do not have to be seen of all cameras calibrated, just 2. If we want to add more camera, our field of view, our working space is bigger because our robot cell is huge. Just add cameras, do a recalibration, use the same model. Very easy, and go for it. All the 4 objects are seen by 2 cameras, so it's working. In this case, we can see just 1 camera. But on the floor, this is a conveyor belt in this example. So having a feature like a moving part, like a conveyor belt, we look on our object. Here, we can calibrate with the calibration plate on the left side a position, and in this case, on the right side, another position. So we have 2 positions that are calibrated, and we know the velocity of the conveyor belt because of maybe we use an encoder, or the velocity is, in the real world, maybe not, but has constant velocity. So we know where the parts are, which distance they moved. We take 2 snapshots, like 2 perspectives, and we also generate a stereo vision. So we have 2 perspectives on the object. Both positions have to be in the field of view of the camera. So also this would work on a conveyor belt with 1 camera. So here, our quadr is going from left to right, and we can detect it. What about adding in this system another camera from a different angle? Having the same scenario, we have 2 positions, 2 calibrated positions. The field of view of both cameras is on both positions. So as a result, we gain with 2 cameras 4 images. This will bring us much higher accuracy, and also we have a much higher detection rate if there are many parts in this scene. Maybe some parts are hidden, occlusions. 2 cameras will solve these problems mostly to see all the parts. In this situation, on the right side, this is a robot. And the robot has a mounted camera. A robot can move. So we can move the robot to different positions. If we know the positions where we take the photos, where we do the snapshot, we can have the calibrated positions with a calibration plate. And later, with a robot and also 1 camera, we could get a multi-view scenario. So also you can imagine about this. But I think there are other options too that you can use.
Maybe to reiterate, the model training is really decoupled from the camera calibration, so it happens before. And you're free to move the cameras around after you trained the model. What that means is, if you're using a robot, for example, and you have a good hand-eye calibration, you could actually move the camera to different positions for every scene that you have. So maybe you have some prior information that tells you something about the scene setup and where to actually look. You can dynamically decide where to move the camera, where to take the pictures, and then run deep 3D matching to find the objects. So that's the sort of dynamic flexibility that you have. And to sum this up, why multi-view? So the method works with a single camera, but we really do not recommend it at this point. To get the full advantage regarding robustness and regarding precision and accuracy, we really recommend to use at least 2 cameras. And that gives you a very high accuracy, practically no false positives. It reduces ambiguities a lot. And you have a very, very flexible field of view and camera setup. So, thank you. It's getting a bit heavy. HALCON already has a few methods for estimating 3D poses. So why do we need a new one? When are the old ones still a practical and a good approach? And when maybe should you turn towards deep 3D matching? Let's have just a quick look at the different methods that we provide so far, and that is surface-based matching. It's planar shape-based matching. It's the gripping point detection, 3D gripping point detection, and shape-based 3D matching. And the first one, surface-based matching, it's one of the classic HALCON approaches. And the main key point of surface-based matching is it does not work on images, but it works on 3D point clouds. So you have a 3D sensor, or you have a multi-view stereo, or just a 2-camera stereo setup that reconstructs the surface scene, the scene surface, sorry. Then surface-based matching can be used to find the positions of CAD files, of CAD models in that point cloud. So that's the key difference to deep 3D matching. You need a surface reconstruction, and you can see that reflective ball up there. It's not always easy. There are some parts, especially reflective metallic parts, but also translucent parts, where it's difficult to get a good surface, even with very, very good 3D sensors. Also, it can be a price point thing. So a 3D sensor is not always cheap, especially if you need a high quality. 2 cameras might be, cheaper. Apart from that, surface-based matching is very fast on the CPU, but it does require that you reduce the scene to the relevant part only. So if there is a large background in the scene, for example, that is captured by your 3D sensor, you need to do some manual pre-processing to remove that background. Otherwise, surface-based matching can become very slow, and it might lead to false positives in the background. So there is some more manual parametrization required, and that is not the case for deep 3D matching. We have planar shape-based matching. The name planar comes from the fact that the object is planar, not that it's searched for in a plane. So we have here a metallic part that was cut through, and this cutting plane is planar, and we have the edges, which are really well defined inside that plane. And we can find the actual 3D position, including possible tilts of the object by using this planar patch of the object. And again, this method is really fast on the CPU. It's based on shape-based matching, also one of the classic HALCON matching methods that we learned about earlier already today. And that means it has the upsides of shape-based matching, which is very, very fast execution time, but also the requirements of shape-based matching, which is that you have very well-defined edges. So the edges of the object here, they are really sharp, and they are good or well visible in the image. If your object does not have these kind of edges, or if the edges are not coplanar, you cannot use this method, unfortunately. The 3D gripping point detection, it's a bit different than all the other methods because it does not use a CAD file, but it also does not give you the 3D poses of the objects, really. What it does give you is points on the surface of the objects where you can grip the object out of a box, for example. It also needs a 3D sensor or some sort of surface reconstruction plus an image. It's a deep learning-based method, and the big advantage really is it can work for a lot of different object types at the same time if you train it well. So think about warehousing. You have a box of parts, and you just want to pick any of those parts out of the box. You don't really care about the pose of this part. Then the 3D gripping point detection is the tool that you can use for that. But again, you will have the object in some arbitrary rotation because we do not get the pose, we just get a point where we can take the object or pick it up. And finally, shape-based 3D matching, it's maybe the one that is closest to deep 3D matching. It also has images or a single image as input, and it finds the 3D position of a part. It's also related to shape-based matching, which again means it can be very fast if parameterized right. But again, it requires clear edges. As you can see here, this is a metallic part that was precisely milled. We have clear angles. They are all really well visible in the image. Compare this to our part where we have rounded edges. This approach would probably not work. And another thing with shape-based 3D matching, it can be extremely fast, but really only if the pose range is small. So if you have a small range of possible rotations for your object, this is the method to go. If you're looking for the full pose range and maybe different distances from the camera, then shape-based 3D matching can become rather slow, and deep 3D matching would be the way to go. So deep 3D matching, it's a very flexible approach. It works for a really large variety of different objects. We've tested it with different geometries, with different surfaces, with different materials, different backgrounds, different light situations. We will see this in a minute, actually. And it's very robust. And this is combined with an automatic data generation. You don't have to label any images. And we have this really flexible camera setup. So these are the advantages of deep 3D matching. Of course, it's a deep learning-based method, so you need some sort of reasonable hardware to execute it in a, let's say, reasonable time frame. Some use cases where it's not suitable to use deep 3D matching. The first one is if your objects are not rigid. So think of organic objects, for example. That's not what we are looking at here. And another case is if you're looking for different objects at the same time. In the current version, HALCON 2411, deep 3D matching looks for a single object type only. So if you're looking for different types at the same time, contact us. Maybe we can figure something out. It's also something we're looking at in the future, but it's not working in the current version.
So after seeing all the other approaches and how deep 3D matching is different, let's go for the inter-workflow, and I want to give you some insights how the system works. First, we have input images. It could be one that we do not recommend because of accuracy. So 1 until n would work. We recommend 2 or more. That's the input. Then on each image, we use our known deep learning detector, and the result of the deep learning detector on each image, so all the parts we find, is the input for our deep learning pose estimation. We're doing this for the first image, and then for the second image, as many we have. With the result of all the poses of all the images, we do some grouping. We look which object in camera 1 is also seen in camera 2, maybe in camera 3, and we will bring them together. And finally, we look locally in the images. We do some refinement to look for features like texture or also edges to make it even more accurate. And finally, as a result, we get poses. If there is no object and we cannot detect 1, 0, or as many as we can detect as are in the image. Let's have a look for an example. Here we see a red box and we have some parts inside. So let's look what our detector will do. We get some region of interest of all the objects we can detect, and this, as I said before, is the input for the pose. The pose estimation, the second neural network, detects the poses. And now imagine we have many images. All images have some poses. And now we bring this information together to get some grouping. That's now the part where it's going rule-based. So here, camera 1 can see an object. The object on the left side cannot be seen of camera 2. And also, camera 2 can see one object in the same field of view like camera 1, and one object we cannot detect in this case. But the one object is in both field of views of these two cameras. We do a grouping, and then in the refinement, we make it even more accurate, and we bring it to result. And here, it's the animated result. So after the theoretically part, let's start to see it live working. Okay, here we have 4 cameras mounted, and here we have our known object in the center, in the field of view of all these 4 cameras. We have 2 lights, and now we do a snapshot by pressing here the button, so we can find it. Adding a second object, we can find. Can turn it around a bit. It's detectable, quite accurate. Let's do some more parts. Maybe a bit overlapping, make it more hard. What will happen? We detect all the parts. What now will happen if we just have 1 camera less in the system? Oh, camera 4 cannot see anything, but all the parts are detected by the other 3 cameras. Let's do it here, for instance, also. So it's really, really, really robust. Bertie told you it doesn't matter what's in the background. Here, I put this on because of contrast for the first example. Let's pick something else, like a carpet. We can detect them. So not a big deal. Just change it again. And add some more parts. We can detect them, and really fast. Bring it more close together. This would make it a bit more difficult. Let's see what happens. Okay, but we can detect almost all. We can detect them. Now let's look for this. So really, really robust. Let's make it a bit more dark. Can you see it in the images? For the camera, there's a small difference, but for the system, it's a deep learning feature. It can adapt, it can handle it. To make it a bit more bright, also, we can detect it. Okay, now let's look. We told you about the bin picking. Here, we have a red box with some parts in it. Maybe some parts cannot be seen more than 50% by a camera, but we have a multi-view system. Some parts are hidden because others are on the top. Let's see what happens. Almost all we can detect. So this would be the situation of bin picking system. Let's switch the software to see it a bit more live, to change the situation, to see it a bit more dynamically. For this, I have here a rotary table that you can follow what happens while it's rotating. Now this we can keep here, on the ground. And let's start. Oh, I think I closed the wrong program. Okay, now let's start. Okay, so we detect our objects, and we can see what happens. Now let's switch the light. Now it's a bit too dark. Now it's working. Let's make it a little bit too bright. Also, the system can handle it. In the morning, Ulf told you about having good light every time the same for solving a situation. In many cases, this is really, really important. And at this system here, deep 3D matching, it's robust if with variations. So maybe in your factory, in the cell, On daylight, it's much brighter. At night, it's darker. Or people will put on the light. So it's quite robust. There's some diffuse light, but let's go for some spotlight. Let's put off this one. That's not the ideal situation. Later, you will see why it's robust. But that's now enough for now. Let's look for some different objects. Here, we have some shiny objects, strong reflective objects. Let's look what happens. It can be detected. To see it a bit better, maybe to see all the parts, which one are more shiny. Can even add more. All the ones I add are shiny. So it's robust for that. So if they vary a bit in color, maybe in texture, we can train it in this direction, and it's working, it's robust. Even in darker scenario. There's a very difficult one. This is transparent. Let's look if we can find this. Another one. So even that is robust. Think about what this means if you maybe have some glass objects or shiny objects, metal, polished objects. The multi-view system, Deep 3D matching, can handle this. Of course, every time it depends. We have to test it first, or you have to test it. You have the software now, the option, the feature. Test it, but we expect that normally it's working. I think the result is quite amazing. But what about if we change boxes? Let's pick up here another box. Here. We can detect the objects. And I enjoy a scenario that is a little bit crazy. So here, it's not a fake, so let's add one part, add a second one, add a third one. Why is it working? Because of the grouping. Maybe you figured out that it was a bit slower, then there's no part in it. Of course, our detector will find the objects. Also, the pose estimation that gets the objects, the region of interest, it will work on it. But the grouping and the refinement will tell you, no. The score will be very low. We cannot find a grouped image, a grouped object, and this will lead that we cannot detect it. Let's make something else a bit more crazy. What's happening if we just put on this part? It's 150% of the size. What will happen? We cannot detect because of the grouping. We are looking for that size, that one, but not for the bigger one. I think we've shown that it's really, really robust.
All right. Let's have a quick look at the final training pipeline, what's actually happening. You need the cut file, we need the surface characteristics, we need the potential symmetries. We run this through the synthetic training generation pipeline. We get 50,000 training images, and we use all that information to train two networks: an object detection network that finds rectangles in images, and the pose estimation network that estimates the rotation of the object in one of these boxes. That's the training part.
Okay, after having the model with both neural networks inside, we just do our calibration very fast. In this case was 1 minute, taking 10 pictures of the 4 cameras, the same field of view with the MVTec calibration plate, and we combine now the information, the positions of the camera with the model. And finally, we just can start with the inferencing. We take the images, we put on our inference, and finally, we get the poses. So that's just it. So very often I was asked, how long does take inference time? We did some benchmark. And I think you really want to know how long it takes. Maybe you got the feeling seeing it. So first time we are showing some benchmarks on this feature. That's it. We had a benchmark, 4 cameras, 5 parts in it, and we had 200 milliseconds on a consumer GPU, a potent one. Here, the RTX 4080, 200 milliseconds. Do you know what that means? 200 milliseconds for getting 5 poses. That's not anymore a bottleneck. The robot has to pick them, has to do some work. So it's very, very short time for this situation. But of course, we cannot interpolate. If we have 10 objects or 20, it's not double time. You have to think about, we know now how it's working. On each camera, each image, we take a photo, snapshot. We just have the detector, and for all objects we can detect in one image, we get the poses. And we have to do this for all the cameras. So it depends. If you want to know it a little bit more clearly, you have to test it, or you have to ask us if we do some setup to get an idea how long it takes. So we did it on other hardware too, an embedded device, a Jetson HX Orin, and it took the same scenario 2 seconds. We wanted to know if it's working on this device. And it's working, it's the proof. 2 seconds is not that much. And the model is quite small. It's about 200 till 300 megabytes. So you can transport it to embedded devices too. And we know, embedded market, the speed is increasing fast. So this number will decrease. It's getting faster. So this is an option. And finally, we used our AI Square interface. We had some optimized algorithms by OpenVINO, and we used it on an i9, on an Intel CPU, and it's 2.5 seconds. Even fast. But why is this also important? Maybe the developer or the application engineer has no GPU in his computer. Like I, on my laptop, do not have two. Sometimes I want to test it just to do a feasibility study or to look if it's working. 2.5 seconds, maybe for an inline application, might be a long time, but for testing, it's quite fast, it's okay, you can do it. So you do not have to buy a special hardware to just test it. This would work. Now, let's see it live, the benchmark tool, to see how long it really takes to get a feeling about. Okay, with one part here, we can detect it. Let's make it a bit more bright to see it better. So it's about 160 milliseconds with one part. Here, I had another evil case, so I added some bit inside the part. Let's do a second one. We detect both. 180 milliseconds. So now you can see in this diagram 20 executions of the inference, and you can see the time of each of one of them. And then we scale it to the maximum to see how long it takes almost. Now let's add parts to get a feeling how long it takes. 4 parts. 230. 6 parts. More parts. Let's see if it's, wait a bit, to get an idea how long it almost takes. Let's now look on 3 cameras. Oh, of course, it's getting faster. Now, I do not have to click for the next view. Now I can do this one. Okay? Even faster. but now sometimes the parts are a bit hidden, or it's getting more difficult to find a field of view for both of the objects. So it's like that. And now let's go for a bit more try-hard case. Okay, having all these objects, of course, it's now half a second, but if the robot has to disassemble all of them, I think he will be quite busy. So in the past, it was a bottleneck. I don't think it's anymore, not in all of the cases. So we will let this here working, and let's go to the final slides.
Just to summarize everything, give us the CAD file. At the moment, we will train the model for you. What you have to do is you have to calibrate your setup, run the inference, and you get the poses. This is the workflow, again, for HALCON 2411. And starting with HALCON 2505, you will also be able to train the models yourself. And to wrap things up, why Deep 3 matching? It finds you 3D poses in 2 or more images. It works with 1. We really recommend to use 2 or more. It's very flexible regarding the camera setup, so you can enlight your field of view, your working area from different directions, for example. It's a huge advantage comparing to just a single 3D sensor, for example. It's very robust thanks to deep learning and thanks to the variety that we introduce using the automatic training data generation and the augmentation during training. It's, I think, reasonably fast for robotic applications on the GPU. Training data is done completely automatic. There is no need for manual labeling. It's 5-minute setup and then quite a few hours on the GPU, but there is no manual work involved anymore. And finally, there is very little parametrization that you have to do. Again, all these examples here run with default parameters. We didn't have to change anything, even if the background changes, if the light changes, if one of the camera fails or anything. It just continues to work.